Hi everyone, welcome to the presentation of this work. My name is Alberto Fuentes-Contreras, and today I'm going to present you the proof of weighting algorithm that has been developed in the last years in order to achieve fairness in CSMA networks by solving cryptographic puzzles. So the main idea behind this proposal is trying to find a mechanism that can improve 802.11 wireless networks so that we can avoid the presence of wireless devices that are modified and tampered and are trying to have access to the wireless channel for longer than they should and try to monopolize on the wireless channel. This work has been developed in conjunction with Miguel Jimenez Gañan, who is my supervisor in these PhD studies that I'm following in Universidad Politécnica de Madrid. So without further ado, I'm just gonna start with a basic introduction on the main ideas behind the problematic and why we thought this could be a great idea to develop. So first of all, we found that there's a lack of mechanisms in 802.11 networks in order to avoid devices from taking control of the channel. So let's imagine a wireless device that has modified drivers, and these drivers contain lower timers, and they have for the different variables they have a higher transmit power. They also contain reduced number of windows in order to wait for the access for the channel, and all these kind of things that can be modified in an easy manner by just analyzing many of the drivers from the main wireless antennas. We could find that this could be a problem and that there should be more attention on these kind of behaviors and how to detect and avoid them. So first of all, we found that there's a lack of proposals to solve these kind of problems. We're calling these kind of devices selfish or greedy devices. And the main reason for that is because they try to be selfish on the access to the channel. They try to be greedy. They try to access and monopolize the channel in order to avoid other users to use it. The main reason or the main objective of these devices could be just to avoid other devices from transmitting, or just basically trying to have a higher throughput through the wireless network. So we find that there has been more advances and developments around other kinds of attacks in a wireless network, like for example authentication attacks. We found WPA2, WPA3, and there's been a lot of analysis on how to try to attack these vulnerable protocols, but there's this huge lack of them for this kind of problem. And it is also, as we mentioned, it's relatively easy to modify the driver. Someone with medium skills could analyze the driver, find those values to be modified, like the amount of windows to wait for transmission, the period for the different timers, and the transmit power. A lot of different variables can be affected depending on the vendor. Also, you have access to more or less, but pretty much there's a lot of things that one can do, right? And finally, we acknowledge that this makes a huge impact in production and enterprise wireless networks. As from the experience from the person that's speaking, I have seen as a network engineer in a lot of customer networks from different vendors, the presence of these kind of attacks, and there has been a lot of issues. In many occasions, the vendor or the partner that's speaking to the network engineer doesn't know what's going on, and in many cases it's quite hard to figure out what's the main problem behind all this, because it is pretty much the last thing that you could think about, right? So this is a big problem. When we analyzed the state of the art, we could find a lot of works. Many of them were on the direction of trying to solve this problem from the point of view of algorithms like Markov chains. For the case of the first reference in this slide, we found that this proposal is very interesting, but it doesn't have the corrective measure that we are trying to provide with the proposal, with our proposal. Also, we found that there's a lot of attempts to try to solve this problem with machine learning algorithms like support vector machines and logic classification. In this kind of cases, we can find that there could be problems regarding the kinds of scenarios that the different algorithms has been exposed, right? So this could be hard to transfer an algorithm trained on a network to work on a different network depending on the different devices, on the different environment, the location, even how the different walls and the different devices are located in the location. So this could be problematic to expand this and transfer this solution to all the different ecosystems. And finally, we have found that by just basically analyzing with data analytics the delays between the transfers and transmissions from the users or the client devices, someone can find anomalies in that regard, and you could try to identify which devices could be behind these selfish behaviors. Alright, so the algorithm that nowadays is permitting the different wireless devices on an 802.11 network to communicate or access the wireless channel is basically CSMA, which is Car Sense Multiple Access. And in this algorithm, basically the client devices need to wait for 13 timers that are fixed, right? So from the spec of the wireless protocol, they have to wait diffs and sieves. The diffs is longer, so basically they need to wait for that prior to transmissions, but for the acknowledgement of the transfers, they need to wait for a shorter timer, which is sieves. And there's also the need for a client device to wait for contention windows if they find the channel being used by other devices when they have waited for the diffs timer and they want to send traffic. So the main problems that we could find with this is that basically the modified wireless driver could provide a selfish device, as we can see in this slide, to have access to a wireless access point. And the main problem is not just that they could have access to a wireless point. If we think about wireless networks that are multi-hop, that they have multi-hops until there's a wired connection, this could even affect even more the congestion of the network by those traversals between the different wireless access points. So we find that a solution for that could be what we have called the POMAC, or proof of waiting medium access control, that basically requires the client device that is wishing to send data to provide a solution to a cryptographic puzzle. And that cryptographic puzzle is basically by using the data from the package that you want to send to the internet, or basically to the access point, they need to find unknowns. That's basically an integer like 1, 2, 3, 4, 5, whatever integer, so that when you calculate the sum of the data and the knowns and you hash that value, you get a certain amount of trailing zeros at the end. So this algorithm is very similar to how Bitcoin or other proof of work cryptocurrencies work, and in this manner these cryptocurrencies have become capable of avoiding any user from trying to spend twice a transaction or trying to send transactions that are fake, right? So in this manner, by just enforcing enough proof of work or enough compute prior to accessing the channel, because they need to dedicate a time in order to find the nodes, that's expected to be a bit of a hard problem. We can make sure that these greedy devices are going to wait for longer. So if they try to just provide a fake proof of waiting solution, the access point is going to avoid the access to the network. It's not gonna forward the traffic towards the next hop, right? So of course they could try to send the traffic to the access point, but the access point is gonna check for that nonce. If that solution for the cryptographic puzzle is wrong, the access point is gonna just basically stop the connection, and it's gonna avoid the client device trying to connect or sending the traffic farther in the network, right? So it's gonna be stopped, congestion is gonna be reduced. One of the properties of this algorithm that we propose is basically the fact that we can adapt this scenario to different amounts of congestion, right? So if we have a higher congestion, we want the devices to wait for longer in order to avoid the high amount of traffic or overload, right? So by increasing the amount of trailing zeros that we are requiring the client devices to provide in their solutions, we can make sure that this congestion environment is not gonna affect these client devices. So basically, as we can see in here, the access point can monitor the congestion and just say, hey, this is the new difficulty to go for. Alright, so how this resolution of a cryptographic puzzle happens on a client device. First of all, when the client device has available data to send, it's gonna start with a nonce of 0, right? It's gonna just sum up the nonce to the data, it's gonna calculate the hash, it's gonna check how many trailing zeros it has at the end, and if it is higher than the difficulty present at the moment in the network, it's gonna try to send the data appended with the nonce to the access point. If it is not, it's gonna try to increment the nonce, and it's gonna try to calculate again the sum, the hash, and the amount of trailing zeros to check if it is higher than the difficulty. If so, it's gonna try to send that again, right? So as we can see, as we increase the difficulty in the network, it is gonna be harder for the client devices. They will need to make more calculations in order to find that nonce. And of course, the device could be lucky, but as we have done some evaluations with practical algorithms that are in use in the ecosystem, we found that the amount of being lucky in this algorithm is not that relevant, so that the algorithm works for most of the time. Like it's not going to affect the performance of the network. Also, the evaluation of this solution from the cryptographic puzzle happens on the access point. How that works is whenever data is received, it's going to get the data. The access point is also going to get the nonce. It's going to make the calculation that has previously done by the client device, and it's going to check if it is higher than difficulty, that amount of trailing zeros. If so, it's going to just route the packet. If it is not higher than the difficulty, it's going to drop the packet. So in order to evaluate how the impact of selfish client devices on the network or greedy devices on the network could be, we develop a simulator that tries to simulate different timers, different amount of contention windows to wait for. You can configure it for having a higher amount of devices, lower amount of devices, so that you can see how it could affect. So in this picture we are seeing an evaluation in which there is one selfish node, that is the node number 1, that is having lower timers than the rest of the nodes, and because of that it has more access to the channel. Their data transmissions are currently happening on higher rates than for the rest of the client devices, and we can also simulate having data to be sent on different intervals. Like for example, we would like to simulate that 1 out of 4 times the client device has data to send, or if we want the client device to send data whenever we start a simulation round. So in this case we chose the latest. Like we want to make sure to evaluate how the client devices, whenever they want to send traffic forever, could behave on this kind of present for selfish nodes, right? So we can see that node 2, for example, is more affected than the rest, and the node number 4 is also a bit affected. So on the right side we provide which is the different color codes for this diagram, but basically one could consider that being red is related to having to drop the connection because the amount of contention windows has gone beyond the maximum, which in 802.11 networks is 7 attempts. And whenever it's yellow, it's something around 2-3 contention windows. Whenever one see that it is light green, it basically means that after the first contention window, the client device was able to send the traffic, right? So in order to try to apply this to a real scenario, we thought about proof of work algorithms that has been on the ecosystem, and we chose the Arduino Coin proof of work algorithm that provides equitative rewards for all the kinds of computing capabilities for the devices. In this manner, we can make sure that even though we have a very high-end device on the wireless network and a very small device on a wireless network, like for example a microcontroller, both devices have the same allowance to access the channel, right? So for these cases, we can see even though the Intel i7 is much more capable than an ESP32 microcontroller, we can see that the reward for those devices is the same a day, right? So that means that we have an algorithm, a proof of work algorithm that cannot be mined as one could do with Bitcoin, right? In Bitcoin, for example, having better GPUs or better ASICs provides the user more capabilities to mine in Bitcoin, but in this case, this is mined using the CPU, right? So we don't get any improvement from having more parallel CPUs or more cores. So one of the main limitations of this proposal is basically that we need to modify the wireless driver in order for this to work. We need to make sure that the access point has the logic to evaluate all the different transmissions from the user, right? The hashes, the nonces, and see if the trailing amount of zeros is higher than the difficulty. We also need to make modifications on the client devices. We need to tell them, hey, prior to sending data, you need to calculate a valid hash, right? That is going to be related with the amount of trailing zeros requested from the access point. Another limitation that we can find is, hey, there's going to be some difficulties on heterogeneous environments, right? Like what happens when we have PDAs, we have mobile phones, we have access points from different vendors. Even though we are using or we're proposing the usage of Arduino Coin, how different capabilities from the hardware is really going to affect this, right? Because we have the evaluations for Arduino Coin for different devices, but we haven't tested for hundreds or thousands of different client devices, cores, CPUs that are available on the market. And finally, this calculation of hashes could reduce significantly the variety of wireless devices, right? Because they need to make calculations that are not expected to be done in the case of CSMA. So some future work lines for this research work could go in the direction of trying to consider other problems to solve instead of trying to find a hash that has a certain amount of trailing zeros by a nonce, right, for the data that the user is trying to send. Like for example, trying to evaluate or calculate the location of the devices in the wireless network, or try to calculate metrics for the wireless usage. In this manner, we can try to make use of this process of finding the hashes, but instead of finding the hashes, just trying to do something useful with for the wireless network. In addition, trying to investigate all algorithms to find better ways to calculate the optimal difficulty, or how to modify the difficulty as the congestion progresses on the network. And finally, try to find a mechanism that doesn't require the client devices to make these calculations, so we can just leave this resolution to an intermediate node they can make that for the user, right? So the client device could associate with one of such devices and would trust that device to provide such values. This could be more useful on environments that has multi-hop wireless networks, like sensor networks, for example. So that is pretty much it. Thank you for your attention. And if you have any question or suggestion for the work, please leave it down in the comment box down below. Thanks.